Hi everybody, my name's Jeff Kotz. I'm here today to talk to you about discrete probability distributions, particularly the binomial probability distribution. If you recognize these slides, it may be because you are familiar with this here textbook, Basic Statistics for Business and Economics by Lind, Marshall, and Wathan. If you don't have the textbook, that's all right. We should be able to get you what you need just from this video. Things we're going to talk about today, we're going to talk about what a probability distribution is, along with defining some of the necessary components, what a random variable is, again, coming back to mutual exclusivity and collective exhaustiveness. We're also going to look at a formula real quick. It's about calculating a mean, otherwise known as an expected value. We're then going to look at a specific type of probability distribution. In this case, it's the binomial probability distribution. We're also going to take a look at how to expand that to an entire binomial probability experiment. If you've looked at chapter 6, you'll notice that there's a lot of things I'm leaving out. I'm leaving out the component on uniform distribution. I'm leaving out the component on Poisson distribution. There's a specific strategy and reasoning behind this. For the material I want to eventually get to, the Poisson and uniform distribution stuff doesn't build there. I'm intending to build on discrete probability distributions to get to continuous probability distributions, which allow us to use the standard normal distribution to make inferences using statistics. But for now, we have to do this. What is a probability distribution? It's a listing of all the outcomes of an experiment and the probability associated with each outcome. As you can see here, we're flipping coins. But this table that you see here is not a probability distribution, primarily because there's no probabilities on this table. The only thing we have here are the 8 possible scenarios where we can have all tails, which means 0 heads. We can have 1 head in a number of different positions. We can have 1 tail in a number of different positions. We can have 3 heads. There's a number of different possibilities that we can get here by taking a single coin and flipping it 3 times. Those possibilities are listed here. So it's a 1 in 8 chance, or 0.125 probability, that we'll get exactly 0 heads. There was one scenario where we got tails, tails, tails. Only one scenario out of the 8 where that happened. There was only one scenario out of the 8 where you got heads, heads, heads. And that's the scenario down at the bottom where it says total number of heads 3. On the right side of this slide, you can see how that gets graphed with a discrete probability distribution there. It's discrete because it's counting. We'll talk about discrete versus continuous in just a second. In a probability distribution, there's a few characteristics, and you're going to see these coming up over and over again, especially as we talk about some of the other ones. But for any probability distribution, one, the probability of a particular outcome must be between 0 and 1 inclusive. That's just how probabilities are defined, as a decimal between 0 and 1. So you can't have a probability be less than 0, because that would mean it's less than impossible, or more than 1, which means it's more than absolute. Doesn't make sense. Two, the outcomes are mutually exclusive events. Getting 1 head or getting 2 heads over the course of 3 coin flips, if you tell me how many you got, you're telling me exactly how many you got. If you got 2 heads out of 3 flips and you told me, oh, I got 1 head, well, you got at least 1 because you got 2. And no one except a jerk is going to say, I got 1 when you really got 2. Lastly, if the list is collectively exhaustive, the sum of the probabilities of the various events is 1. Now that's important because that allows us to use the complement rule, which we use almost exclusively throughout these questions. Other variables that still need definition, a random variable. A random variable is a quantity resulting from an experiment that by chance can assume different values. So in that coin flip example, we can see here we have 4 different random variables. We can have a random variable equal 0 because we got 0 heads. We can see the random variable can result in 1 head, it can result in 2 heads, it can result in 3 heads. So that random variable x can take on 4 possible values. There's 2 different types of random variables. Here in chapter 6, we're going to stick exclusively to discrete random variables, things that we can count. That allows us to look at the binomial probability distribution. A discrete random variable can only assume clearly separated values, usually as the result of counting something. Whereas a continuous random variable, which we'll see in chapter 7, can assume an infinite number of values, usually within a given range. It is often the result of some type of measurement. We're not talking about continuous here. We're just talking about discrete in chapter 6. So suffice it to say, if we're talking about discrete random variables, we're talking about things where you can count the number of occurrences. For example, the number of students in a class, the number of children in a family, the number of cars entering a car wash, the number of home mortgages approved by something, something, something bank. In other words, they're things you can count. They are not continuous like the length of a song on an album, or the weight of a student, or the temperature outside. Those things are continuous values. Here we're focused on discrete. So here's another probability distribution, another specific one. Doesn't involve coins or dice or pulling marbles from a bag. It involves a guy named John from Pelican Ford. John has free time on his hands and develops this probability distribution and says, tomorrow there are 5 possibilities for the number of cars I'm going to sell. Now remember, it's discrete, John thinks. It's discrete, so I'm not going to sell half a car. It's possible that John sells 0 cars, 1, 2, 3, or 4. So for that random variable x, there's 5 possible values, 0, 1, 2, 3, and 4. And John says there's a 10% or 0.1 probability that I will sell 0 cars tomorrow. There's a 20% or 0.2 probability that I will sell exactly 1 car. There is a 0.3 or 30% chance that I will sell exactly 2. A 30% chance I'll sell exactly 3, and a 10% chance I'll sell exactly 4. Now, those are mutually exclusive because exactly 3 does not overlap with exactly 2, with exactly 4, etc. And it's exhaustive. You can see if you add up those mutually exclusive events, you can sum up the probability and get 1. So this is pretty good. But now I want to know is that although John has lots of free times for creating probability distributions, I want to know in the simplest fashion, John, buddy, how many cars do you think you're going to sell tomorrow? And there's a number of different ways we can think about that result here. First, we can see that the modal probabilities, the highest probabilities, are associated with selling 2 or associated with selling 3 cars. In fact, there seems to be a 60% chance that either 2 or 3 cars will get sold. So it seems like that would be a pretty good estimate. But also, we're able to calculate the mean of this distribution using this formula right here. The mean of a probability distribution generally tells us about the central tendency of it, but what's super awesome about this formula is that it gives us expected value, and that's most commonly how this particular formula is used or described. So mu, and again, the symbol for mean here, is equal to big sig, or capital sigma, meaning we're going to add up a bunch of stuff. The things we're going to add up is the product between the random variable x and its associated probability. So we multiply x times p of x, the random variable number, times the probability it happens. And then we do that for each random variable we have. So we're going to have a bunch of products, and that's what this formula says, is we're going to add up a bunch of products. When we add them all up, don't average, rookie mistake, just add them up, you see that we can get the mean of a probability distribution here. So at the bottom right corner, once all the arithmetic is done, we see that mu equals 2.1. That means that John expects to sell about 2 cars tomorrow, which is consistent with the way we looked at that probability distribution before. Another type, a specific type of probability distribution, is the binomial probability distribution. And you'll see that some of these things do look similar to the other stuff we looked at before. Particular characteristics of the binomial probability distribution is that there's only two possible outcomes of a particular trial of an experiment, and we often call those success or failure. Note, we're not adding any value judgment to success or failure. In one of the later examples we'll see, we're going to discuss a call being dropped on a cell phone. Well, I wouldn't call it successful if a call got dropped, but we can define success in terms of the likelihood of dropping a call. Don't want to get too far ahead, just to emphasize again the point that success and failure are the two possible outcomes. That's why we call it binomial. Two possible outcomes which we'll define as success and failure. Two, those outcomes are mutually exclusive. You can't both succeed and fail, especially statistically. Three, the random variable is a result of counts. Again, this has got to be a discrete rather than a continuous probability distribution. Four, each trial is independent of any other trial. So we know the coin has no memory. The dice have no memory. So each roll does not have an effect on the roll that comes after or even the roll that came before. It doesn't work like that. Each trial we're talking about is independent. For an entire binomial probability experiment, we're going to see most of the same things, but there's one thing that we add to this that really makes it different. So an outcome on, number one, the outcome on each trial of an experiment is classified into one of two mutually exclusive categories, a success or a failure. We already said that. Here's where the experiment thing really takes hold. We're going to talk about the random variable counts the number of successes in a fixed number of trials. The first example, the coin flip. We said we flipped it 3 times. We had a fixed number of trials. Or if I'm going to flip a coin 10 times or flip a coin 20 times or roll the dice 10 times, whatever I'm going to do for a binomial probability experiment, I have to tell you how many times I'm going to do it. So let's say I flip a coin, an unbiased coin, with a 50% probability of getting ahead. And I flip that coin twice. The expected value, or mean, will be 1. In other words, I expect if I flip a coin twice that I'm going to get 1 head. If I flip that coin 100 times, then I'm likely to expect 50 heads. That's what the formula tells me. That's the mean. That's the expected value. In the first case, I had a fixed number of 2 trials. In the second example, I had a fixed 100 trials. The number of trials is important. We actually give that number a letter. We call it n for the count or number. Third, the probability of success and failure stay the same for each trial. Again, this goes back to independence. We are not drawing a king from the deck without replacing it. Nothing like that. Each specific trial has the same probability. We're just sort of repeating it. Or sorry, each event. Or yeah, each trial. No, each trial was right. You have a size of the trial. The trials, each of those trials are independent. Hey, it's what I just said, meaning the outcome of one trial does not affect the outcome of the next. The key here is that we're talking about a specific number of trials. Now, if we want to use the formula, that's the nitty gritty for us. So if we want to ever execute it, here's the formula. So the probability for some random variable x. Now we're going to put a number in for x. There's 3 parts to this formula that's on top. The first part is NCX, or N choose X. That's something that came out of chapter 5 that I chose not to get in deep with. If we want to use that part of the formula, we can see it at the bottom. It's n factorial divided by r factorial times n minus r factorial, that whole quantity. Replace the r with the x. That formula is in Excel as equals combin, C-O-M-B-I-N. You put your parentheses in there. It's in the TI-80 whatever you have, as if you hit, I believe, the math button, which generally resides in the middle column, and then you're going to look across the top menu there and likely find something that says prob, and you're likely going to drop down to where it says NCR, or not NPR or NCX. Those are, and not the one with the P. P's permutation. You want C for combination. Anyway, the first part is saying do this combination part. The second part of the formula is you take pi, or your success probability, and you raise it to x. In other words, the number of successes that you are asking about. So if I say I'm going to flip a coin 10 times, well, 10 is n. X has to be the exact number of successes that I'm looking for. The third part is, the first part's the combination, the second part is pi to the x. The third part is you take the complement of pi, or 1 minus pi, and you raise it to a power of n minus x. So what that is the number of failures you expect. The first part tells us about combinations. The second part says, if I want this many successes, I need to have this thing happen so many times. In other words, I need to have pi, or my probability of success, occur as many times as I need it to succeed. X, pi to the x. The third part of the formula says, well, for every other trial in this fixed number of trials, that needs to fail in order for me to have exactly X number of successes. So now we're going to get back to how important the exact part is. This first part of the formula, the combination, tells us about the number of different possibilities of this thing occurring. The second part says, I want exactly this many successes given this probability. The third part says, well, let's take the complement of everything else that could happen, and it needs to occur n minus x, or every other trial in the number of trials. The formula is super useful because it allows you to calculate specific probabilities for, specific probabilities for any number of random variables, giving any number of probabilities of successes, and that's super cool. You can even do that in Excel. There's a couple different formulas which you might need to use. Modern versions of Excel have equals, binom, like binomial, the first 5 letters, binom, dist, then you put in an array and stuff like that. Or you have to put an n and the pi and stuff like that. Or binom dist, which is binomdist, but you don't include the dot. Same sort of thing. We'll see another example listed later when I talk a little bit about Excel. Anyway, here's an example. We got through that binomial probability formula part. Here's an example. It says there are 5 flights daily from Pittsburgh via U.S. Airways into the Bradford Regional Airport in Pennsylvania. Bradford is sort of north central, Pittsburgh is southwest. Suppose that the probability that any flight arrives late is 0.2. What is the probability that none of the flights arrive late today? When you see that executed over here with the formula, what I want to do is point out the essential pieces of information here, and there are 3. 1, what is n? What is the fixed number of trials? In this case, we say that there are 5 trials, because there are 5 daily flights. 2, what is the probability of success? Now remember, success and failure, however we define them, don't have a value judgment or good or bad. All we're saying is that this is what we define for success. And the success here is a flight arriving late. So pi is 0.2, n is 5, pi is 0.2. Lastly, I need to know what x is. X is the probability that none arrive late today. None is 0. We need to do a little check just to verify that our successes are lined up, because sometimes you'll see the question ask, what is the probability that none are on time today? Well, that would be the complement of all of them, or at least one being late. None on time is the complement of at least one being late. That wording always gets mixed up, so you got to be careful about that. But in this case, my success is arriving late, and I'm asking about the probability that none arrive late. So I've got consistency between my probability of success, pi, and x, the random variable indicating the number of successes. If you execute it here, you see that the probability, I'll leave the arithmetic to you. This is what happens when you put that stuff in there. 5c0 equals 1. Anything choose 0 is 1. The number of successes, 0.2 raised to the 0, because we're looking for probability of success, 0.2 raised to no successes, and then the complement occurring 5 times. 0.3277. We want to look at that graphically. It looks like this, where the probability table is on the left-hand side using the Excel formula I referenced earlier, where the number 0 is our random variable, and the probability 0.327680, or 3277, is the exact probability that exactly 0 will arrive late. The probability that exactly 1 arrives late is 0.4096. Exactly 2 arrive late, 0.2048, etc., etc. And that's how it gets graphed on the bar chart next to it, on that visualization there. We can see that the height goes up to just above 0.3 for 0 late flights, and that's what makes sense from the table on the side over there. Now that we're able to see that we can use this formula to create specific tables here, we're going to be able to answer a lot more questions. Answering one question saying, oh, it's exactly, for exactly 0 late flights, here's the probability for that. Sometimes, a lot of times, we're more concerned about a range of values. In continuous probability distributions, it's always the case. But for binomial probability distributions, sometimes we want to know what about 0 or 1, or between 1 and 4, or that none of them are on time. Lots of different ways we can ask these questions. Another question we can ask is, given this information about how many flights can we expect to be late? That goes back to John's question. John at the car dealership said this is the probability distribution of how many of these cars I expect to sell, which is fantastic. But me, I just want to know, hey man, how many cars do you think you're going to sell? Well, hey man, how many flights do you think are going to be late? It's calculating the mean. It's calculating the expected value. Now, you remember when we did this earlier for John, it looked a little something like this, where we had to take x times p of x, repeat that for all the different numbers of cars sold, add them up, then you get mu. On the right-hand side here, you can see the list of the characteristics for a binomial probability experiment. Not all of those are met with John's example. We don't know anything about how many people he's talking to, about the success or failure on any given trial to create this probability distribution. We don't have any of the necessary information. It's not a binomial probability distribution. If you want to calculate the mean of any probability distribution, including John's here, which is sort of subjective probabilities, let's face it, this is just what he thinks, then we have to use this formula of big sig of x pi xpx. We have to do that whole thing. But if you've got a binomial probability distribution, that's your formula. The average or expected value from a binomial probability distribution is n times pi. That's it. The number of trials times the probability of success for any one trial. Because each of those trials is independent, nothing's affecting anything else, and it's all just the samey there. Mu equals n times pi, and that's it. Super easy. So if we take this late flights example, we can do the whole xpx thing here, and if we use that formula at the bottom and we make that column we add up all of those xpx's, mu does equal 1. Or you can use the simple formula, say, given that this is a binomial probability, I can take n and I can multiply it times pi, and I get 1, and it's so much easier. I think that's pretty rad. But you can only do that if it's a binomial probability distribution. Here's another example that I referenced earlier. In a region of the country, 5% of all cell phone calls are dropped. What is the probability that out of 6 selected calls, none were dropped? Always go through and find the 3 essential pieces of information. First of all, what's our fixed number of trials? It says, what is the probability out of 6 randomly selected calls? Out of 6. So that's our number of trials. The probability of success, again, while it's not success for me to drop a call, that's how we're defining success. Success is a dropped call, 0.05. The thing we're asking about is what's the probability that none of these calls were dropped? So there's a number of different ways that we can go about answering this question. If we went back to our basic knowledge in chapter 5 about how independent events and how you calculate the probability of those things, we can say, well, if each call is independent and the probability that a call gets dropped is 0.05, I'm sorry, the probability the call gets dropped is 0.05. I know that the probability the call doesn't get dropped is 0.95. And the probability that none of them get dropped is the complement times the complement times the complement to the 6th power. It starts to get a bit complicated. But given that we now have this given information, n, pi, and x, we can access the answers a number of different ways. In your textbook here, on, believe it's page 550, you will see what you see on this screen. The binomial distribution table, and there's different tables for different fixed number of trials. This is the table for n equals 6 because I said there were 6 trials. Had I said that there were 7 or 8 calls, I would have to go to the table with 7 or 8, where n equals. The second part is pi, or the probability. The columns indicate the probability of success. So I start by finding my table because I have 6 trials, and then I find the column that I'm going to use based on the probability of success. In this case, the probability of success is 0.05, so I use that column. The last thing I need to know is what x value am I solving for? Well, I said that I'm looking for the probability that no calls were dropped. Well, I go to 0 here because that's my x value. And then I go to that column that I said, and hey, that thing in the white rectangle inside the pink rectangle inside the other white rectangle says 0.735. That's the answer. The answer you get if you use that complicated formula before. It's the answer you get if you do it in Excel. It's the same answer. If I ask another question, an alternate question, a complementary question, I might say, what's the probability that out of 6 randomly selected calls, so again, n equals 6, what's the probability that exactly 1, exactly 2, exactly 3, exactly 4, exactly 5, exactly 6 are dropped? There's an or between 5 and 6, and I'm asking about them collectively. In other words, I'm asking about the complement of no calls getting dropped. Here's where we start to be able to do something with this question. So the probability that no calls get dropped is 0.735, which means that the probability of a call getting dropped, or 2 calls or 3 calls, I don't know, all I care is that at least 1 call gets dropped, is the complement, which I could find either by adding up all those things in blue down there, or I could take 1 minus 0.735. That's the complement rule. That's how I'm more likely to use this. Because as much as it's good to know the probability that a call doesn't get dropped, I'd like to know, well, what's the probability that a call does get dropped? Increasing the number of calls, the fixed number of trials, the n value, if I increase that number, I'm certainly going to be increasing the probability of a dropped calls because there's more potential calls to be dropped. Other ways that this probability distribution can change shape, you can see here below. Now this is holding n constant. So we're saying we've still got the fixed number of trials. In this case, it's always n equals 10. It says that across there. But what we vary is pi, or the probability of success. We'll start 4 over where pi equals 0.5 because that one's symmetrical. And the symmetry should make sense because we're talking about an equal probability for success or failure, no matter how we define each. One direction is the same as going in the other direction. So you can have symmetrical binomial probability distributions. Oftentimes, though, they aren't. They might look kind of normal, like the one on the far right here, where the probability of success is 0.7. Hey, and look, where's the mode? The mode is at 7. It's also what the average would be. Given that it's a binomial probability distribution, the expected value is pi times n. 0.7 of 10 is 7. And that's where the big spike is there. Don't confuse, though, mode and mean, because they're not the same thing. Well, they happen to share visually that position on these graphs. We can look at any other of these. For example, the one on the far left here that says pi is 0.05. The probability of success is almost 0. I'll take 10 cracks at it. How many do I think I'm going to get right there? I'm not likely to succeed, which is why there's that huge spike at 0. That indicates to me that it's not likely that I'm going to succeed at all. The probability of success is very low. I don't have enough trials to even muster up one success. Well, it's still likely. It's still likely that I might get a success. Not very likely that I'll get 2 or 3 or any more than that. But yeah, it's somewhat likely that I'll get a success, around 30%. Another way that these distributions can change shape is if you hold the uh, if you hold the probability of success constant and you vary the n, or the fixed number of trials, you can see how those changes shapes here. We can work backwards and try to figure out exactly what the probability of success here. I might think that it's about 0.1, but I'll leave that to you to guess and figure out why. You can ask me if you want to. But we can see is the number of trials increases from left to right. That the number of successes also increases. For example, on the far left, if I have 7 trials, this says that it's not very likely that I succeed. Given 7 trials, it doesn't even say that I'm going to get more than 4 successes. But if I go to the right side and say, you know what, if you take 40 tries at it, it looks like there's even some possibility that I'll get 7, 8, or 9 successes. That's how these things vary in shape, that you can maintain the probability of success. And if you increase the number of trials, you also increase the potential number of successes, as well as the probability of those successes. On the left-hand side, again, there's no probability, 0 probability, no chance that I'll get 5 successes. But by the time I give myself 40 cracks at it on the right-hand side here, I can see the probability is almost 0.18. 40 cracks at it is almost a 20% chance that I'll get exactly 5 of them right. 5 successes. One last example, and then we'll wrap it up. This binomial probability distribution example talks about the Illinois Department of Transportation, concluding that 76.2% of front seat occupants use seat belts. They did the research and found that to be the case. A sample of 12 vehicles is selected, cars passing by, let's presume. What's the probability that the front seat occupants in exactly 7 are wearing seatbelts? So we've got n, the number of trials, which is 12. We're looking at 12 cars. We've got pi, the probability of success is 0.762, 76.2%. And we have x, our random variable, equal to 7. We want to know what's the probability of exactly 7 successes. Well, here you go. If you do this formula, 12C7 is 792. There's 792 ways to choose 7 things from 12. We see that the first probability is pi to the x, 0.762 to the 7, times the probability of the complement raised to whatever's left over. In other words, the complement of 0.762 raised to the 5th, or 12 minus 7. Hey, the exact probability to answer this question is 0.0902. In other words, there's about a 9% chance that given a sample of 12 fixed trials and a success rate of 0.762, there's a 9% chance exactly 7 people are wearing seatbelts. Very specific answer. Though I might be more concerned about this question. What's the probability the front seat occupants in at least 7 of the 12 vehicles are wearing seatbelts? At least 7 means 7 or 8. 8's at least 7, or 9, or 10, or 11, or 12. All of those are at least 7. 6 and lower are not. 0 to 6 is the complement of 7 to 12. Less than 6 is less than 7 is the complement of 7 or more. One way we can calculate this answer is to do out each of them. So the probability of x equals 7, which we saw, 0.0902, plus p of 8, p of 9, p of 10. And yeah, we add all those things together because they're mutually exclusive. The probabilities, there's no overlap, there's no joint probabilities, no general rule of addition. We can just add them up. We add up all those probabilities, 0.9562. So there's about a 96% chance that at least 7 cars have a front seat passenger wearing a seatbelt. That's a pretty good probability. Much easier way to calculate this. We've seen Excel before, but if you use that binomial distribution function, which you can actually have that first argument in that function be what's in the left-hand column, you can set up your own binomial probability table here. And you can say 7 or more is the sum of those things in that formula. That's a lot more easy, I think, to use Excel in that fashion than it is to calculate each and every one of those probabilities by hand. So now we know that a probability distribution has certain characteristics. We talk about the mutual exclusivity and the collective exhaustiveness ad nauseum at this point. I've used the term random variable multiple times today. Hopefully we understand that that's a random outcome from a number of trials. It's the random number that's associated with the counts of things. We know the expected value, or mu, is equal to big sig times xpx. We've looked at binomial probability distributions in a lot of different ways that we can use tables or Excel to get answers to questions here. We also know that the expected value, or mean, of a binomial probability distribution is nothing more than n times pi. We've gone through some details of a full binomial probability experiment, talking about having a fixed number of trials with a success probability and targeting a specific number of successes. That's the stuff you need to know out of Chapter 6. It's always so hard to say goodbye. Bye.